front or?
I have to press it now.
Okay. Okay. Um, so I will continue to discuss today the straightforward empirical analysis that the data can be subjected to, assuming equilibrium. So later we'll turn to the issues to whether actually, to what degree the equilibrium is achieved in reactions. But you know, the success of the statistical descriptions with regard to anything in nature is relies on the fact that we are looking at systems or at observables which don't provide exact information about the system, but allow for many options for the system to take and still reproduce those observables. And so if you look at various details, you may always claim, oh, the system is not fully equilibrated. But the success of statistical descriptions relies on the fact that you look at reduced information about the system, where you project the system just on a certain set of limited observables, such as momentum distributions, which particles reach at the end of the reaction. And you don't look about all the details, or you know what happened where, to the left or right, earlier, later, what path led to this particular state, and so on. Other than momentum or spectra, you know, the variables which are fairly coarse, which reduce the information, which provide a coarse description of the system, are particle multiplicities. So let's look at, you know, if you assume equilibrium, you get information about spectra. Let's look at yields in equilibrium, particle yields in equilibrium. So if you ask about the total number of particles coming out in certain types of events, so this is just an integral over momenta of the distribution of Maxwellian form that we wrote. And so you integrate a Gaussian. So we have a prefactor v over 2 pi cubed, statistical factor g. And then we have a factor of chemical potential plus binding over t, and finally the true integral e to the minus p squared over 2 mx t. So what is the integral of this Gaussian factor? Pi over, so this pi over, if you have an integral e to the minus alpha x squared, this is pi over alpha, right? So alpha here is 1 over, so it will be 2mx t to the power 1/2, 3/2 because we have 3. Okay. So then you can combine those 2 pi and 2 pi there, and for nx you get gv square root of mx t over 2 pi 3 halves e to the mu x plus bx over t. Okay. So if you assume that a region in the reaction which produces particle has reached equilibrium, then given that chemical potentials are related to nucleon potentials, you can use just the few parameters. So you use V, T, mu n, mu p. They are obliged to describe all particle yields from your source. Okay. Moreover, let's say very often in an experiment, you will maybe not covering all angles. So maybe you don't see, all leaks through which particles can go out. You look at some region, and you look what is the yield in that particular angular range, and you cannot tell. I mean, you could maybe extrapolate the angles. You could argue what the total number should be, but you can look at the ratio of the yields if you're in a certain range of the angles. So you can look at what a yield ratio, say nx to ny. Okay. If you take a ratio, then the ratio should be describable. V drops out as an overall normalization factor, the volume of the source. And this you should be able to describe just in terms of T, mu n, and mu p. Okay? And very often people don't make a distinction between neutrons and protons. They say, the system is approximately symmetric. Maybe the chemical potentials are about the same. And replace both chemical potentials just with one chemical potential of nucleons. And so then all yields should be describable just in terms of two parameters only. And so you looking at the yields ratio, you can fit them. You can try to fit them with only one temperature. These kind of parameters are called freeze-out parameters. That describes the situation when the system was breaking up and particles going out to detectors. So these might be called freeze-out parameters, because you may say, oh, during the reaction, during the early stages, maybe temperature was larger. I mean, chemical potential was larger. But these are freeze-out parameters, which you describe final yields with. And another adjective which can be added is chemical freeze-out. And the concept is the following, is that as the reaction progresses, you have processes which are inelastic. So when particles break up, maybe pions are created. The particles, form a deuteron. Deuteron breaks up, and so on. And when those reactions stop, you reach those parameters describe the yields. But later, maybe a little bit longer, interactions still continue, but are softer, and they are don't manage to break particles, don't manage to change the composition. Then we can change the spectra of the emitted particles. So you may talk about the chemical freeze-out temperature, and you may talk about kinematic freeze-out temperature. That will be one which you will use to describe spectra. And kinematic, which do you expect to be larger if they are different? Which temperature should be larger? Why? It's later, and as the system expands, it tends to cool. Okay. Expands, T kinematic describes spectra. Elastic processes continue longer than inelastic. Okay. Now let's make, so in a moment I'll show you data, the results from analyzing data. Can one make a simple estimate for the temperature that one should reach? What sort of temperature can you? So we established, so let's consider symmetric collision, okay? In a symmetric collision, let's say that it's at some lab energy per nucleon, okay? In the center of mass, you will have per nucleon what kind of energy? 1/4. And how should this be related to temperature? 3/2 T. Note, I mean, I didn't make it explicit. We always use, in nuclear physics, we use fundamental, so-called fundamental temperature measured in units of energy. So KB is 1, and Boltzmann constant is 1. So it will be 3/2 T, okay? So with this, T should be equal to 2/3 E lab over 4. So this should be 1/6 of laboratory energy per nucleon. Okay, that's a simple estimate. So let's look at data and see how this compares in particular. So these are temperatures extracted from analyzing yields. So this is Hong from FOPI collaboration. And I think the data are not just from FOPI, he just make some compilation overlaid with his own analysis. So, so these are the temperatures extracted from the yield. So you know, not surprisingly, temperatures rise as energy rises. Let's compare this to our simple estimate. So at 100 MeV, we would expect how much of the temperature? 16. Okay, so somewhere here. Where should we reach? So he goes up here, it's nearly 100. Where should we reach 100 according to our estimate? at 600 MeV. So the simple estimate gave roughly, it was not dramatically off, but the data look a little bit different. And so we have deviation at low energies and a deviation at high energies. At high energies, of course, it looks like it will become more and more dramatic. So what are those deviations associated with? That's true. If the motion is not fully thermalized, then there is energy stored in the longitudinal motion, and less will be, there will be no full isotropization, so more energy in longitudinal motion than in transverse. That's one source. So then this could explain this deviation. What about this one here? Why do you have more temperature? So actually the error, the potential, the potential error is made here. See, if you make this estimate here, you assume that every nucleon is free. And we are at low energies, we have tons of clusters. So basically what you have is full kinetic energy will be ELAB over 4, okay? But this will be equal to if you have certain number of particles, let's call it n, okay, script n. Each of them may have kinetic energy 3½ T. Then if you divide it by A, you will have ELAB over 4A is n over A 3½ T. So T will be equal to ELAB over 6A times A over N. If the number of clusters is smaller than A, the temperature can go up. Of course, if you go to low energy, you also need to consider binding before and after. So things get more complicated, but this gives you the sense of why temperature can go up beyond the simple estimate. So in this particular case here, so longitudinal motion is important. There's another factor that's important if you go to high energy that will prevent temperature from growing indiscriminately. What is that? So the temperature, even if the system equilibrated, even if you got rid of the excess longitudinal motion, the temperature cannot climb indiscriminately. So this is because once you put temperature significant, make temperature, so temperature of what 100 is comparable to the mass of what particle? Pion. Becomes comparable to pion mass, so it becomes very easy to produce pions. And then it goes higher up than other mesons. So around here, the energy goes into the production of new particles. New particles, especially mesons, especially pi mesons. So actually the freeze-out temperatures, even if you go to ultra-relativistic energies, the temperatures never exceed about 170 MeV because of the new particle production. And people may argue, maybe you create core gluon plasma and so on, but this is basically similar physics. You just produce very many new degrees of freedom. About 170 MeV. So let's look how the model performs. Because this is the parameter which is extracted, but it's extracted from fitting. And so here you have data and model at different temperatures of the system. I believe this was gold on gold. And so 1 GeV, 1.5 GeV, 2 GeV. And in that analysis also effort was made to identify the number of delta resonances at freeze out. That's a little bit model dependent analysis, but you also have ETAs, eta mesons, pi zero mesons, and deuterons to nucleons. And you can see that this model with those, basically with two parameters for the ratios at each of the energies performs very well. And you can extract the chemical potentials, you can extract temperatures. The chemical potentials here are baryonic chemical potentials. So chemical potential is energy. You can principally use, for everyday chemical potentials, you can use some reference energy. But in analyzing data when inelastic processes are present that can lead to the new particles, you analyze, you take the chemical potential is absolute. That is in energy. Energy is when you take particle energy, you write it as mass of the particle plus kinetic energy minus minus. So chemical potential includes the mass. So for that reason, the baryonic chemical potentials are of the order of close to the to baryonic mass, so 700 MeV, 800 MeV. And then once you get these freeze-out parameters, you can compare many different reactions. And let's see. So here you have a phase diagram. So with the chemical potential at zero temperature for nuclei is equal to nucleonic mass. That's atomic mass unit. These are the some of the data which were shown in the other figure. So as you heat the system, temperature goes up, but chemical potential goes down. And here you have the freeze out at ultra-relativistic energy and hypothetically the transition to core gluon plasma. So as you go up with energy, you will drift with freeze-out parameters this way. And around here, you will have the region of the phase transition. the liquid gas phase transition. So located somewhere here. Okay. All right. Any questions, comments? Okay. The yields depend on the factors which are activity, which is chemical potential divided, exponential of chemical potential divided by temperature. And tied to the activity is, or to the ratio of chemical potential of temperature is entropy. So let's look at entropy in a nucleonic gas. Anybody remembers Sackur-Tetrode relation from statistical physics? Pardon? Is what? Minus t? Minus t log z. Where Sackur-Tetrode says S is equal particle number. So if we have this A times, there is a logarithm, but you can also express it as mu over t, because mu over t can be expressed in terms of logarithm with the activity factor. It says 5/2 minus mu over t. It's just very simple. Or normally we will be interested in quantitative entropy per particle. It's 5/2 minus mu over t. So entropy is interesting if you want to describe this kind of system, because it tells you about the level of equilibration. For example, entropy will be higher if you thermalize longitudinal motion completely than if you don't. If the system behaves hydrodynamically, entropy will be lower than if it's completely randomized, and so on. So order yields lower entropy. So the entropy itself can be determined from this chemical potential over T, I'll write it as mu n, can be determined from particle ratios. So let's look in particular at number of deuterons and number of protons. So number of deuterons is, can you tell me in the thermal model? V 2 pi cubed times G. What is G for deuterons? 3. So this is 2s plus 1, spin is 1 for deuteron, so it's 3 times what factor? M deuteron times T divided by 2 pi to the power 3/2. Go ahead. This is oh yeah, that's right. You're right. We should get rid of this. Yeah, that's it. What about protons? And proton T over 2 pi 3/2. Well, we forgot something. Chemical potential. E to the mu d plus binding by T, and here e to the mu n divided by T. Oops. So now let's make no distinction between neutrons and protons. So then mu d we can write as 2 mu n. Md is 2 mu n, and Mp is also mu n, Mn. Bd over T, or assume the temperature is high enough that we can put it to 0. And then Nd over Np is so here we have 2 mu n we divide, so 2 mu n minus mu n over T. All factors cancel. Md over Mp to the power 3/2. The spin factors 3/2. So this will become e to the mu n over T. This will be 3/2 times 2 to the 3/2. So this is 3 square root of 2 e to the mu n over T. So e to the mu n over T becomes Nd over 3 square root of 2 Np. And our Sackur-Tetrode relation becomes equal to 5/2 minus log okay. So let's the variable part of this is Nd over Np. This we can calculate log once for all and combine it with this 5/2. So this will give us 5/2 plus log of 3 times square root of 2. So we get and the formula S over A is 3.95 minus log of Nd over Np. Okay, so this Notice that this formula is somewhat perturbative because we calculate chemical potential taking the ratio of deuterons to protons, but we calculated the entropies if we only had nucleons. So this will work if deuterons there are not too many deuterons in, so they are just admixture, which we can use to calculate assess the chemical potential. But you can do better. I mean, following the same idea, you can include deuterons or other particles, and people have developed other models. But in general, what will stay is that chemical potential can be obtained from the ratio of deuterons to protons, or any other two particles which differ by 1 unit of mass, and you can use it to estimate the entropy. Okay. How does it work? So let's see. So what I'll show you is actually the so this is entropy calculated in different ways from in the niobium collision. The centrality is assessed by looking at the number of protons emitted into wide angles. So these would be participant protons. So which end of the axis represents the most central collisions, and which end of the axis represents most peripheral? Can you tell me? Where are central and where are peripheral collisions in here? Right under the central. Because then you have most protons emitted to wide angles. This is most peripheral. So the points indicate the entropy calculated in different ways. So it includes the ratio of deuterons to protons. It includes some more elaborate formulas where more particles are taken into account. It also includes a testing with a transport model, I believe like this point, where you actually calculate the entropy from, you know everything about the system, so you can calculate the entropy directly. And you find that this formula more or less works. Okay? One should say that entropy is very forgiving. This is because basically entropy assesses the logarithm of the probability distribution in the system. If you make a small error under logarithm tames that error. So you can make big changes under the logarithm. This doesn't change much the outcome. So entropy is very safe quantity. Where's the deuteron ratio to proton ratio largest, and where is it smallest? If you can look at the formula, you can look at the figure. the difference is larger in the peripheral. So there are few deuterons in the peripheral collisions, more deuterons per proton in central. And you can understand it in such a way that there are relatively few protons emitted into wide angles in a peripheral collision. So the phase space is sparse. When phase space is sparse, the deuteron spectrum will go like a square of the proton spectrum. If proton spectrum is sparse, the deuteron spectrum is even sparser. Okay, goes like a square. So if when there are many protons emitted to wide angles, then the proton spectrum is intense, and you take something intense to a power, you get many. So the deuterons are more abundant here and less abundant over there. So relatively many deuterons at wide angles. And here you have few deuterons. Okay. Next figure will actually show comparison. So the points is entropy extracted in different ways from data. Maybe also transport calculation. But this is realistic entropy. Extracted from data and semi-realistic models. This is as a function of beam energy. This is all niobium plus niobium reactions. Is central. And the dashed lines are two limiting models. So this one is a hydrodynamic model. So this model assumes that that collisions can be, so nuclei can be described as fluids. And this one is a pure fireball model, meaning complete thermalization. And a hydrodynamic model is not, not a complete Wacom model. The point is the following: is any system big enough where mean free path becomes short compared to the size of the system will behave hydrodynamically. Okay, so if you had nuclei that could be made big enough, if you didn't have the problem of Coulomb breakup and fissioning of the nuclei, and nuclei could be made big, then eventually for big enough sizes, hydrodynamic model would apply. Okay, but nuclei are small, so hydrodynamics never applies. Hydrodynamics means ordered motion, and in ordered motion, entropy is limited. Pure fireball, you have complete thermalization. All energy is thermalized, and the data show you actually realities in between. Okay. Obviously, you cannot have a hydrodynamic model, but you also don't get quite to the complete thermalization. Okay. So even though it works, the thermal model describes data, portions of the data well, and so on, there is more, okay? This is a situation where eventually we may get to there. So this is in a situation you have two media in the center of mass, going with the center of mass velocity, and in the middle, if the mean free path is short enough, you will have matter which is stopped. When this speed exceeds the speed of sound, these discontinuities have the nature of the shock fronts. And what actually happens in a nuclear reaction is you have this kind of development towards this kind of situation. The problem is these shock fronts have a width which is of the order of the mean free path, or several mean free paths, and this becomes comparable to the size of the nucleus. So if nuclei were big, could contain many more mean free paths, you'd have this situation, and this entropy which is represented here by the dashed line is the entropy you would have had in that stopped matter. Okay, but the system is too small, and so this hydrodynamic picture never fully develops. You just have the system tries to develop shock fronts and tries to develop this region of stopped matter, but never gets there, because by that time the reaction ends. Okay. Now, so this is a thermodynamic model in application to, or thermodynamic concepts applied to yields. Now, we started by discussing the spectra. So I told you that the scaling of the spectra can be used to deduce spectra of particles that are not measured. And one spectrum which always is difficult to measure is the spectrum of neutrons. So when you have ability to measure neutron spectra, you can actually test this hypothesis that everything scales, and you can actually deduce neutron spectra when you cannot. So this was recently done in a tin-on-tin experiment. So this is tin-on-tin at 50 MeV per nucleon, and I think the main author is Hayek-Ski. And you have spectra here of different particles. So you have, alphas, helions, tritons, deuterons, neutrons, protons, tritons, helions, alphas. And then the green line represents two spectra. One is our neutrons, which are measured. So green points are neutrons, which are measured directly. And the crosses are neutrons deduced, I believe, from the combination of a triton, helion, and proton spectrum. Maybe deuteron too, I don't remember already. So these are deduced, these crosses are deduced using the scaling, and the green ones are measured directly. And as you can see, there's a agreement which is just astounding, a few percent. Okay. A crosses reconstructed. So, which indeed shows that you may succeed in doing the impossible. Okay, I think questions. Go ahead. I think so. I think in this paper there were other, they did various combinations, and it all looked good. It's not perfect, but usually you will struggle in the regions where, let's say, different types of sources overlap. So different sources contribute. So if you're in a region where one type of physics dominates, then this will tend to work. If you have secondary decays from cold sources, then that may fail. Okay, anything else? Uh-huh. This is energy in the center of mass of the system, of the emitted particles. System CM, and this will be emission around 90-degree region, so in perpendicular direction. Okay, anything else? All right, so we'll do the break. Yeah. Oh, go ahead. Uh-huh. So one example of the scaling that I have seen. So although I'll talk, after the break about a little bit about the scaling. So this scaling follows from in the thermodynamic model. You arrive at that scaling. The scaling works better than the thermodynamic model itself. So it may work in a situation where thermodynamic model doesn't work, or maybe the thermodynamic model works, but situation is more complicated, like you don't have one source. And I've seen it work, there's a concept which is based on this scaling, which is called isoscaling, and it's associated with difference between neutron and proton chemical potentials, and I've seen that isoscaling applied to deep inelastic reactions, the emission from deep inelastic reactions, and it worked in that region. So in the context of your interest, yes, one should have keep the eyes open. It may work. Anything else? Go ahead. Yes. So the reason why it studies the symmetric reactions is literally for, because as I mentioned, it's that the center of mass for analysis is obvious. But yes, it should work in other reactions as well. You may have a more complicated combination of sources in asymmetric reactions. But also asymmetric reactions, from the point of view of myself, who doesn't do reactions, just a spectator, the asymmetric reactions are at an opportunity, because people have beaten symmetric reactions to death, but have done not much. They have done some preliminary work on asymmetric and then left them for the symmetric because life is easier. So I think there are opportunities in asymmetric reactions. Okay, anything else? Go ahead. It's multiplicity. It's just like n. It's just multiplicity. Distribution of multiplicity in an event per energy and spherical angle. So if you multiply it by the cone in the omega, you would get the number of particles in that, and integrate it over, and you have the number of particles in that cone per event. So one should say that at the beginning of analysis of Hawaiian collisions, people used cross sections for, because this was the tradition brought in from peripheral reactions, that you express everything in cross sections. And so then if you integrated a quantity, this would give you multiplicity times cross section for the specific reaction. But later it became clear, that most natural quantity is how many particles you get straightforward to talk about multiplicity in an event. Okay. So we do the break? Yeah. Okay. You were wasting your time here.
Fine here?
Yeah. Thank you.
You stay up to the end of the week?
I leave on Saturday. I think, yeah.
But you know Florence, or is it?
Yes,
Yes,
sure, of course. No, I know more than I want need to.